All right, so we just did a little bit talking about domains and everything like that. I'm gonna do one more example of that, and then we're gonna start talking about operations between rational functions, right? So yesterday we talked about how we could do operations between polynomials, right? Addition, subtraction, multiplication, division. We did all sorts of things like that. Now we're gonna do it specifically between rational functions. So first I wanna do an example. If I want to find the domain of, say, the square root of x divided by x minus 5. Oh Lord, it's raining. So if I wanted to find the domain of this function, first I have to consider where the denominator does not equal 0, but I have another constraint on top of that. This can't be negative. So I'm restricted to the fact that x has to be greater than or equal to 0. That's what the top part tells me. And the bottom part tells me that x cannot equal 5. So before I try to write out my domain, I'm going to put everything on a number line to kind of visualize it. So I have to start at 0, but it can be equal to 0. Right, if I put 0 here, I just get 0 divided by negative 5 is still 0, so we're good. But I can't equal 5, so I'm going to have to take that out. I got everything between those, and everything up past that. And so first I'll write it in interval notation. So this is going to be, I can smell the rain. That's crazy. Can anyone else smell the rain? When I moved up to Illinois, people thought I was crazy. They were like, what do you mean you can smell the rain? I'm like, I'm from Georgia. Of course I can smell the rain. Anyways. So I can start at 0, be equal to 0. I go up to 5, but I do not include it. So I've got an open circle here, right, because I can't equal 5. And with that, I'm going to go from 5 off to infinity. So that's my domain. Now in set notation, this is going to be, I'll say right here, the domain of root x over x minus 5 equals, maybe I'll do r first, all real numbers except for the set of x such that x is negative or x equals 5. So that would be it in set notation. Remember, this is the real numbers minus the set of all x such that x is less than 0 or x is equal to 5. You can open those, it's fine. So for example, if x equals 5, I get square root of 5 over 0. I can't divide by 0. If x is negative, say negative 2, I get the square root of negative 2, which is undefined when we're talking about polynomials over the real numbers. We can all agree with that? Any questions about this? Again, it's just the notation that looks confusing. That's how all of mathematics is. We try to write things as simply as possible and it gets more confusing. Yes?
How do you know when to put x versus just 2? Like in the real numbers minus that.
And what do you mean?
Like in the other one we had the domain was real numbers minus 2.
And negative, because it was only 2 points. This one's infinitely many points. I could have rewritten this as the set of all r greater than or equal to 0. That's a bit of notation mathematicians use. Minus 5. For instance, those are terrible braces. So that's what this notation would mean. Sometimes people also use the notation plus, but that can mean different things. So if I wanted to just exclude this 1 point, I also have to mention that it has to be greater than or equal to 0. With the other example, since I was only taking out those 2 points, it was very easy for me to write everything but those 2 points. This is r minus the points 2 and negative 2. Versus here, I have to take out an entire interval, which is everything that's negative, and that point, which I could rewrite as this, but you have to understand that this part actually just means the first part right here. That's a good question, though. It's just notation. This is a bit more convenient instead of introducing new notation, but if you can get comfortable with this notation, you can use this instead. Any other questions? We'll now talk about operations between rational functions. There's one T in operations. Thank you, Corey. Between rationals. So for instance, say I want to add 2 ones. All of the rest of this is going to be just examples that will help you understand how to work through some problems. So we'll start with addition. Say our example is we want to add 3 over x minus 1 with x over x plus 2. Remember when we add fractions, if I have a over b plus c over d, I have to cross multiply. I get ad plus bc over bd. So I have to do the same thing here. I have to cross multiply here, here, and then down there. So I get 3 times x plus 2. I'm just going to leave as that for now. Plus x times x minus 1. And then because this process puts them over the same denominator, I can just write it as one line and then put one denominator. And then x minus 1 times x plus 2. If you're confused as to why we have to do this, revisit the notes that we took proving that this is how we have to do this, and that's how we get this right here. I can then kind of expand this out real quick. That's 3x plus 6 plus x squared minus x. I'm not going to touch the denominator yet. I'm going to leave it as is. All right, so all I did was I multiplied this 3 in here, multiplied this x into those 2. And then I'm going to rewrite this in our standard form where we descend by the orders of exponents. So I've got x squared plus 2x plus 6 all over x minus 1 times x plus 2. And now this revisits Irene's question of why can't we just do it with a graphing calculator? Why can't we just factor with a graphing calculator? I need to factor this top part because it's going to probably cancel with one of these. Good Lord, it's raining cats and dogs like that. Do y'all know where the expression "it's raining cats and dogs" comes from? Used to in old times where houses were made really crappily, in the rafters where it was dry, cats and dogs could get in there, but if it rained really hard, they didn't want to be hit by all that rain, so they would jump into the living room or the house or whatever. And so people would say it's raining so hard, it's raining cats and dogs, because cats and dogs were coming out of the sky. There's your little bit of fact there. All right, I want to factor this top part. So I'll go over here and I'll factor it. X squared plus 2x plus 6. I want the factors of 6 that add to 2. This is going to be 6, 1, 2, and 3. Oh, that doesn't actually have any really nice factors. Nope. And I don't think I factored it well either. No, because it doesn't have nice factors. What are the factors of this? 4b squared. Okay, this doesn't actually have any real solutions. If I try to set this equal to 0, they're all imaginary. So there are no factors here. We will not be factoring that. So I already knew we will not be answering your question yet. This is as simple as it can get to. I have 2 points that cannot be solutions of this. Those 2 points are where this equals 0 and where this equals 0. Those cannot be in my domain. So the domain of my original thing, which is 3 over x minus 1 plus x over x plus 2, is all the real numbers except for where this equals 0. When does x minus 1 equal 0? 1. And where does x plus 2 equal 0?
2.
Negative 2. Right. If you need to for any reason, you just do x minus 1 equals 0, so x equals 1. X plus 2 equals 0, so x equals minus 2. And that's our domain. Again, it's easier for me to do it with a number line before I do interval notation. So I get everything but the points, what, negative 2 and 1. Where this is minus infinity, this is infinity. So my interval is minus infinity up to negative 2. Again, open circle. From negative 2 to 1, open circles, and then from 1 to infinity. And I didn't put my union symbol there. So I can say that. Any questions about this? So really the complicated part here was just simplifying this thing. Once we simplified it, we just had to pick out the parts that make the denominator equal to 0, and our domain is everything but those. All right. That example's kind of complicated. We will do. Yeah, we'll do an example that answers Irony's question. Does everyone have this copied down? I'll give you all a couple. Yeah, I'll give you all a couple seconds to write it. There's a lot of stuff on the board. I get to park really close though because I work here, so I just run out the back door and I'm good. I don't know how close y'all get to park, but I don't think it's as close as I do. Unless y'all park right there on the other side of the faculty parking lot, in which case you do. Otherwise, rip. I remember my first day of undergrad, it rained so hard and I showed up soaking wet to my history class. Hated my history teacher, she was actually racist, but that's a different story.
Oh.
Her last name was Butts. B-U-T-T-S, kind of deserved. But she had the AC cranked as high as possible, and the only seat was for me to sit right beside the AC. And I got so sick because of it, because I was soaking wet and had to sit next to that AC, and it was awful. Moral of the story is own and bring an umbrella with you wherever you can. This problem is going to involve instead polynomial multiplication or fraction multiplication. Remember when we multiply fractions, we can literally just multiply directly across. The multiplication works the way we think it does. So we'll let our example be x squared plus 2x minus 3 over x squared plus 8x plus 16 times 3x plus 12 over x minus 1. Thanks. Now before I do anything here, I want to factor the top and the bottom to simplify things. So I'm going to first factor x squared plus 2x minus 3. Factors of minus 3 include 1 and negative 3, and negative 1, or 3 and negative 1. Which of these add to positive 2? 3 and negative 1. So I get x plus 3 times x minus 1. So that's that first part. I need to factor this bottom part now. X squared plus 8x plus 16. Factors of 16 are 1, 2, 4, and 8. And 16. With 16, 8, 4, 2, and 1. Which of these pairs adds to 8? 4 plus 4. So I get x plus 4 times x plus 4. All right. Is that supposed to be 3x plus 1? No, it's 3x plus 12. What is a common factor of 3x and 12? 3. I'm left with x plus 4. And then on the bottom, I get x minus 1. Now here's the answer to your question, Irony. The reason that we factored out like this is because I have a lot of cancellation that happens. I cancel out this 1 with this one. I cancel out this x plus 4 with this x plus 4. So now I'm left with x plus 3 times 3 over x plus 4, which is 3x plus 9 over x plus 4. Or I could leave it factored as 3 times x plus 3 over x plus 4, which actually that's what I'll do. So instead of saying, oh, well actually 1 and negative 4 are not the possible numbers, I know that 1 actually is possible because it canceled with this factor up here. So my domain is just everything except for where this equals 0. X plus 4 equals 0 at negative 4. So my domain of this long complicated thing, which I'm just going to call f of x, is all the real numbers except for negative 4. And as an interval, negative infinity up to negative 4, union negative 4 off to infinity. Any questions about this example? It seems long and complicated. You just have to sit down and work through every part individually and try to, instead of trying to do a bunch of parts at once.
The middle part, can you like re-explain the middle part?
This part?
Yeah, like how you got
I factored this top part of the fraction right here. I factored into this, so I replaced it with that. I factored the bottom part of the fraction into this and replaced it with that. And in this part, I saw the common multiple was 3, so I factored it out. Then, because I'm doing a bunch of multiplication, I can do cancellation. This x plus 4 cancels with this one. This x minus 1 cancels with this one. I can only do that because it's multiplication. If it was addition, I wouldn't be able to do that. So because I have that multiplication there, it works. I canceled those out and got my answer. Any other questions? All right. Another example for y'all. And then we will introduce one topic if I can squeeze it in before 1:30. If not, we will save it for tomorrow because it actually works decently well with tomorrow's lesson anyways. Actually, I probably will save it for tomorrow. What if I want to simplify? I'll actually do this one. X over y plus 1 all over 1 minus x over y. This seems really complicated. I have a fraction of fractions. I just want to deal with each part separately. This first one, I'm going to rewrite it. I have x over y plus 1. I want to combine those, so I need to turn this into y over y so they have the same denominator. And then I can turn it into one fraction. Any questions about this part? I can do the bottom part the same way. I have 1 minus x over y. I want to get the same denominator, so I'm going to make this y over y. Y over y minus x over y. And since they're over the same denominator, I can write it as one fraction. So I converted the top function into just one fraction and the bottom function into just one fraction. Now I want to recombine those. My top fraction is x plus y over y, and that's divided by y minus x over y. That looks really complicated though. Remember when I do division of fractions, a over b divided by c over d is the same thing as a over b times flipping that second fraction, d over c. So I can instead rewrite all of this as x plus y over y times the reciprocal of this fraction, y over y minus x. And I have some really nice cancellation that happens. I can cancel, oh, not that part, but that's fine. I can cancel the y on the top and the bottom because I have multiplication in between them. So when I do that, I get x plus y over y minus x, which greatly simplifies this result. It looks a lot nicer. So all this is to say this is equal to x plus y over y minus x. I'm not worried about the domain for right now. We've done enough with domains. Are there any questions about this?
Is this abstract or this is like a...
This is a real example.
Oh.
These are two different variables. It just happens to be that it's only variables, but I like have a plus one and I have a minus one. But this isn't a general case. This is a real example. All right. Let's see. I'll do one more example. It's a little complicated, but it might be good for y'all to see it, or at least have it in your notes to refer to later, or have it on video to refer to later. That sounded like those crossing, the crosswalks. You have to press the button and go, wait. At University of Tennessee in Knoxville, if you press them too many times, they get mad at you. So you press it, it'll go wait, 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 and it'll say wait to cross the street. I went there for a conference a couple of years ago, and it was really fun. We just kept pressing those.
That makes more sense with the formula.
This next one, I don't think y'all are gonna like this example because it's complicated, but it is useful to see it. So just bear with me. One plus x squared to the 1/2 minus x squared times 1 plus x squared to the minus 1/2 all over 1 plus x squared. Just looking at it, that's a terrible problem. That is like something that you'd see in a really complicated mechanics problem in a physics class or something. But we want to factor it out. It does factor to a pretty nice result, I'd say, but we have to factor it. I kind of have a common factor here, more or less. I'm going to rewrite this x to the 1/2 as 1 plus x to the minus 1/2 times 1 plus x. Remember, when I have a common base, a to the n times b, or not, I'll do that the other way around. X to the a times x to the b, that's x to the a plus b. So I can add their exponents if they have a common base. Negative 1/2 plus 1, technically a 1 there, equals 1/2. So I've kind of split it apart. Minus x squared times 1 plus x squared to the minus 1/2. And can you see why I rewrote it that way? I have this term to the minus 1/2, and I have that term to the minus 1/2 there. So I finally have a common factor between the two things. And then this is all over 1 plus x squared. I can factor out this 1 plus x squared all to the minus 1/2. So I'll do that. There should be a squared here. Yep. Factoring that out, I have left over this 1 plus x squared to the 1, and this minus x squared. And then the bottom stays the same. Now notice in here I have x squared minus x, so that's just going to cancel. And then I have this times the remainder, which is 1. Something times 1 is itself, so that works out pretty nicely. I just get 1 plus x squared to the minus 1/2 over 1 plus x squared. And I can simplify this one step further. Remember that x to a negative exponent is equal to 1 over x to that exponent. Right, negative exponents tell me to put it in the denominator. I've got a negative exponent here, so I'm going to move it to the denominator. I get 1 over 1 plus x squared now to the positive 1/2 because I put it in the denominator times 1 plus x squared. And then lastly, I have a common base multiplied with some exponents. I can revisit this rule right here. What is 1/2 plus 1? 1.5 or 3/2. So my final answer, and this looks kind of silly because everything's going on. I'll separate those out. 1 over 1 plus x squared to the 3/2. So I'll write that out as the final answer. 1 over 1 plus x squared to the 3/2. So that was a really complicated example, but it included a couple of important things. It included this exponent's power, and it included splitting this up to get a common factor. We're not going to do a lot of examples that are that complicated. There sure as heck will not be an example that complicated on any of your tests. More so, it just incorporates a lot of things that are useful to see. If any of y'all ever have to take a course on electromagnetic theory, if you want to major in physics or electrical engineering or anything like that, this is actually very similar to a very common result that you see when you're talking about the electric force between 2 points. So that is decently useful for y'all. That's all I have for y'all today. If y'all have questions, of course you can come by my office hours. Y'all can email me, anything like that. We will pick up with the rest of this tomorrow and then introduce complex numbers. So for the rest of y'all's day, try to stay dry.